the first question involves several parts regarding amino acids, right? Which are no different from any other polyprotic acid. So when you're solving an amino acid problem, you're going to model it as some polyprotic acid, such as H2A or H3A, etc. So I'm just going to start here by first drawing the structure for these. And you don't have to know these structures by heart. You'll be given them, but you should be able to interpret them. So all of the amino acids have two basic functional groups, one of which is an amine. So proline has an amine that's in a cyclic structure. And when fully protonated, any amine takes on a positive charge or is an ammonium ion.
No.
And then the carboxylic acid is going to be fully protonated as OH in neutral. So when you're coming up with an abbreviation for a polyprotic acid here, what you want to do is think about how many pKa's there are. That will be the number of acidic H's that can be ionized. The number of H's in each formula will be the number of pKa's given. And in other words, you don't need to know which H's are acidic as long as you know that there's one that corresponds to every nitrogen that's basic, and there's one that corresponds to every carboxyl group. Okay, so in this case, we have a diprotic acid H2A. Finally, the other part of the abbreviation that you must get right to answer questions about net charge is the number of positive charges when fully protonated. And that is equal to the number of basic nitrogen atoms. And for every amino acid, amino means nitrogen, so there'll be at least one positive charge, and there's just one here for proline. So we're going to model that as H2A. And aspartic acid also has a carboxyl group that is alpha to an amino group, but the side chain of the functional group here is a second acidic carboxylic acid. And the pKa that is closest to 2 always goes with the carboxylic acid. The pKa closest to 10, 9 or 10, goes with the ammonium ion. And whatever the other pKa is that's not 2 and it's not 10, that's going to go with the side chain. So there was not a third acidic proton for proline, but there is for aspartate or aspartic acid. So we're going to model this now as H3A, and it has one positive charge. So finally, arginine is another triprotic acid. And the proton with a pKa approximately 2 is the carboxyl again. When it's approximately 9, it's the ammonium ion. And then the side chain is a basic functional group. And when fully protonated, this nitrogen takes on a positive charge. And so that must be the other pKa, which is 12.5. So this is also a triprotic acid, H3A, but it bears 1, 2 positive charges, and therefore it would start out as 2+. Okay, so the first question regards proline. And we want to know what the net charge of the predominant form of proline is at pH 4. And I say the predominant form because at any pH, you generally have more than one species present, but you can think of all of the equilibria of this polyprotic acid is a number line to determine the predominant or the majority in solution. So H2A, you dissociate to form HA, which is the neutral compound or the Zwitter ion, and that will then dissociate again to form A minus. And remember that the diprotic form is an acid. The fully deprotonated form is a base. And the intermediate form, which is a Zwitter ion, is both an acid and a base, or it is amphiprotic. And the way that you can think of these in terms of their relative concentrations at a fixed pH is simply by putting the pKa's from lowest to highest, right, most to least acidic, like a number line here. And if the pH, of course, were more acidic than 1.99, then you would have the fully protonated, or the most acidic form. If the pH were greater than 10.6, then you'd have majority A minus. And the majority at any pH between those values is going to be the Zwitter ion. And the pH is between 1.99 and 10.6. So at pH 4, that means we have HA as the majority, and therefore the net charge of the predominant form is 0. Okay. If you were asked a question about the second most predominant form, then you would find the closest pKa to 4. And that pKa that's closer is the 1.99. And that would tell you that H2A is the second most predominant, or you have a buffer of those two. In other words, we can now rank the relative concentrations, and you would find that at pH 4, the concentration of HA is greater than the concentration of H2A, which is greater by far than the concentration of A minus. We'll do more of that in a minute with arginine when we sketch the fractional curve. Okay, so the next one deals now with aspartic acid hydrochloride. And hydrochloride means has been fully protonated with HCl or by HCl. So the fully protonated form of aspartic acid is H3A plus. And we are titrating that with a strong base. Before I do the titration, I'm just simply going to write out all of these equilibria up here to the side, and then I'll write the net titration reaction below. So H3A becomes H2A, the Zwitter ion becomes HA minus, and that fully becomes A2 minus when it's all the way deprotonated. And then the pKa's here are 1.99, 3.90, and 10. So we're starting with a fully protonated form, so I should take H3A and do a reaction with sodium hydroxide. And I'm just going to leave off the sodium as it's a weak spectator ion. So we have a strong base, right? And a strong base indicates a one-way irreversible arrow, which should tell you to set up an initial change final table. So hydroxide deprotonates the first of 3 protons, okay, for 100% of the H3A molecules because it is a strong base. And whenever hydroxide's a reactant, that means that water will be a product. And we're given mole values, and generally in these ICF tables, they are not equilibrium processes, right? It's an irreversible or a one-way arrow. And therefore, you're generally going to work in moles or millimoles. Whereas in an ice table, you would work in concentration. So I'm just going to plug millimole values in here. So you have 50 millimoles of H3A and twice as much strong base. Water is not going to affect the pH, and at the instant when we mix these together, we assume that we have not yet done any acid-base reaction, so we start with no diprotic acid. But now, because it's a one-way arrow, it's going to be a limiting reagent problem, where the reaction runs until the limiting triprotic acid runs out. And that gives extra 50 millimoles of strong base. And you make an equal amount of the diprotic acid. And so now to decide what to do next, you must think about the characteristics of the analytes that remain in the solution. So you have plenty of strong base remaining. It's going to continue to deprotonate something. You also have an Amphiprotic species that is both an acid and a base. We knew that this was Amphiprotic, both acid and base, because it is between pKa values, okay? In other words, it could go backwards to act as a base, or it could go forwards and act as an acid. So it can do either if it's sitting by itself in water, but when it's in the presence of a strong base, it will behave as an acid and be deprotonated, which means that I write a second reaction now, where H2A is now deprotonated by a strong base to form the monoprotic acid, also irreversibly, because you have a strong base. And therefore another ICF table, where the final contents of the first table become the initial contents of the next. And this is now a reaction where we have no limiting reactant, and therefore we make HA minus only in the end. So we have 50 millimoles of HA minus. And HA minus is also Amphiprotic. It's both an acid and a base, because HA minus, right, is found here between pKa's 2 and 3. So it has two characteristics, or sometimes it can go backwards and act as a base. Sometimes it can go forwards and act as an acid. So now it's by itself in water, which means that there is no strong base to tell it what to do. So it does both reactions. In other words, HA minus is producing hydroxide in some amount, and it's producing hydronium. And therefore, the pH is a balance of those two. And when you have an Amphiprotic species that's alone in water, you can't simply solve for the pH with the Henderson-Hasselbalch equation, right? It's not a buffer. You can't solve for the pH with one ice table because it's really doing two reactions. It's making both hydroxide and hydronium. you must solve for the pH by averaging the pKa's. And the pKa's that surround that intermediate are 3.9 and 10.00. So the average of those is going to give you pH. So I get 6.95. And this problem is the second equivalence point problem. Where you started with 2 equivalents, or 2 times as much strong base as your weak acid. So as long as it's not the last equivalence point, you can always find that pH by averaging the appropriate pKa's, those that surround this intermediate that we have. Okay, so the next problem is dealing with the third amino acid, arginine, and I want to sketch a fractional composition curve as a function of pH, and I'm going to write out all of the species for arginine above. So arginine, if you look back to our original abbreviation, is a triprotic acid with 2 positive charges when fully protonated. And it is going to become a diprotic monocation, and then a zwitterion, and then A-. And the pKa's there were 2.19, so 2.17, 9.08, and 12.48. So we should see 4 different species on this fractional curve. And remember that alpha is equal to, or the symbol for fraction. And at any one time, the fraction of all 4 species sums to 1. So the y-axis here, or the dependent variable, is alpha, and we'll pay close attention to this 50-50 mark. And then the independent variable is pH, as we are increasing pH to the right, and it's becoming more basic. And so at very low pH, okay, when the pH is less than 2.17, we're going to have a majority of the triprotic acid. And that should start out at about 100%. So let me color these so we can keep track. So H3A should originate at 100% and quickly deprotonate. And that one was an acid. And it will always have this sigmoidal shape in the curve. As the pH approaches 2.17, we are going to begin to get a significant concentration of the diprotic acid. And they will intersect at 50-50. So that gives a rise in H2A concentration, followed by a symmetrical fall. And as H2A is deprotonated, it will form HA, especially as the pH reaches 9.08. And therefore, we'll have another parabolic one, where HA eventually is deprotonated to give A-. And finally, at very high pH, we're going to fully titrate it to give the conjugate base, and that will be predominant at all pH values above 12.48. So I'll write out the predominant species for each of these. And you should know that when you have 50-50 of each of them, that's a perfect buffer. So when you have equal amounts of di and triprotic acid, that's when the pH is the first pKa. That's a half equivalence point pH. When you have equal amounts of di and monoprotic acid, the pH is the second pKa. And when the monoprotic and fully basic forms are equal, the pH is 12.48. And we can now see that the point at which we have approximately 100% diprotic acid is the average of pKa's 1 and 2. So that's 5.63. And we have approximately 100% of the zwitterion, at 10.78. So the amphiprotic species on these curves will always be parabolic because they are dual in their functionality, or they can increase and then give off a proton, so they can decrease in concentration. But the fully basic form and the fully acidic form are just sigmoidal, or their curves look like an S shape. Okay, so be able to fill out those diagrams and label them at the appropriate pH values on the x-axis. And you should know that if you were to change the pH to pOH, then everything would flip. And you would be going from A- to HA to H2A, etc., as you go from left to right. Okay. So the only other curve that you're likely to be tested on in terms of acid base is when we do a titration. So now I'm going to take fully deprotonated proline. And remember, proline I modeled as H2A+. And we said it has pKa values of 1.99 and 10.6. But now I'm taking the fully deprotonated form, or A-. And I'm going to titrate that with HCl. And one equivalent of HCl will take it to the first equivalence point, or give you the monoprotic acid. And the next equivalent of HCl would take you to the end point, or the diprotic acid. So there should be two equivalence points on this graph. And the axes for titration plot are fundamentally different from those of the fractional composition plot, where now we have pH as a dependent variable, and I'm going to use volume of HCl as the independent variable. So we're told that HCl, right, or the concentration of HCl from the stock solution is equal to 5 times the concentration of fully deprotonated proline in the solution to which we're adding HCl. Now, at the first equivalence point, that means that we are going to have moles of HCl equal to moles of A minus. And another way of writing that is that the molarity of HCl times the volume of HCl is equal to the molarity of A minus times the volume of A minus. Well, we don't know either molarity, but we do know their relative ratio. 5 times as concentrated is the HCl. So I can now say, well, whatever the molarity of A minus is, that times 5 is the molarity of HCl. And if you now want to simplify this as much as possible, then you cross out the molarity of A minus, and you can see that the volume of HCl required to get to the first equivalence point is the volume of A minus divided by 5. Which means the volume of HCl for the second equivalence point is double that, or 2/5 the volume of the base A minus. Okay, so let me sketch the shape here, and then we'll label those various volume values. So we are going to start at a basic pH, right? We're starting with the fully deprotonated form, and the pH is going to drop slightly and hit a buffer, and then it is going to hit a titrate, or hit an equivalence point of the titration, and then another buffer region and another equivalence point. So the titration equivalence points are at the inflection points here. So when the volume of HCl is 1/5 of the volume of A minus, that's the first equivalence. And when the volume of HCl times 2/5, or sorry, a volume of A minus times 2/5 is equal to HCl, or we've doubled it, that's the second equivalence point. Which means that the first half equivalence point is going to be when we have volume of A minus over 10. I just divided that by 2. First half equivalence. And the second half equivalence will be when we have volume of A minus divided by, let's see, divided by 7.5. You can simplify that further. Okay, so let's talk about what the major species is at each of these various regions of the curve. So originally, you start with the fully deprotonated form, A minus. And the way that you would solve any pH problem before you add HCl, when you just have that weak base, is an ice table, with Kb1. Once you have titrated some of it and you reach this buffer region, now you are going to have some A- remaining, but you've also made some of the conjugate acid, HA. And therefore, a mixture of two weak conjugate species is a buffer where the pH is solved for using the Henderson-Hasselbalch equation and the appropriate pKa, which is the higher pKa because we're working backwards, pKa at 10.6. And right here at the half equivalence point, you have 50-50 of each one, and the Henderson-Hasselbalch equation will dissolve to just give you a simple pH equal to pKa. So at this first equivalence point, keep it in red, we have now titrated fully to HA, right? Every single A- molecule has been protonated once, and your major species is HA. And that's where the pH is the average of the pKa's, because we have an Amphiprotic species alone. The next buffer region is reached by titrating with another limiting amount of HCl so that we have some HA left over, but we've also made some H2A+. So in that buffer, you also use the Henderson-Hasselbalch equation with the log of the base over the acid. But here, the pKa is much lower. It's 1.99. And now we can see graphically that at the first equivalence point, we should be an average between the two half equivalence point pHs. So that is going to be 6.30. Just average the pKa's. Okay, and so then at the final equivalence point, we have added 2 protons to every molecule in solution. It's all H2A, and therefore it's a weak acid, and you would do an ice table with Ka1. It's the most acidic form. Beyond that, if you have to, you'll just do a strong acid problem. So imagine that we added extra HCl. So now we're in the excess strong acid region. And that's just a simple strong acid problem where you find the amount of HCl that's in excess and you take negative log of its molarity. So you should be able to solve for the pH along each part of this curve, and drawing the curve and labeling it in a very descriptive manner like I've done will give you an expectation for what a reasonable pH value is, and you can double check your math that way. Okay, so that's your diprotic titration with a weak base and a strong acid. This one happened to be an amino acid, but it's the same math for any polyprotic acid. Okay, so the next one is dealing with proline, aspartate, and arginine, all at pH 5, and they are loaded onto and separated via cation-exchange resin. So we have a strongly acidic resin, and cation exchange means that cations stick to the stationary phase. So the stationary phase must be negatively charged at pH 5. So it was acidic, but it's been deprotonated. And the structure of the stationary phase is this. It's generally a sulfonic acid. Where the pKa for the proton that was here is -2, so it's deprotonated to any reasonable pH value. And therefore, any of the cations, I'm just going to say, for example, H3A 2 plus, or H2A plus, etc., those are going to stick. So the most positively charged cation at pH 5 will be most strongly retained. So what we can do here is determine what the net charge is for each of the amino acids that we're separating, okay? So I've already done this for some of them. So I'm going to copy and paste the Proline one here. And I'll just highlight that Proline at pH 5 is mostly in the HA form, okay, or the majority of it's neutral. And then aspartate, we wrote this one up above. So it was a triprotic acid with one positive charge initially. So at pH 5, aspartate has passed 2 of the pKa values, and the major form of aspartate will be HA minus. That's between 3.9 and 10. And then I'll just write out the arginine one again. Arginine was H3A 2 plus with pKa's of 2.17, 9.08, and 12.48. So now you can see that the major species for arginine is H2A plus. So the arginine is the most positively charged, while the aspartate is the most negatively charged. That's synonymous with saying the most basic is arginine, or it retains the proton, and the most acidic was aspartic acid, so it became anionic aspartate. So the next question is a brief review of some chromatographic mathematical parameters that describe how weakly or strongly retained various analytes are. Remember that Kpart has to do with concentration of some analyte in the stationary phase over the concentration of that analyte in the mobile phase, or a higher partition coefficient means a greater affinity that that analyte has for the stationary phase, SP. And we know now that in this experiment that it has a greater amount of net positive charge if it has an affinity for the negatively charged stationary phase. So the Kpart value for arginine, because it is +1 net charge at pH 5, is going to be greater than the Kpart value of Proline, which is net neutral, and that will be greater than the Kpart value of aspartate. And recall that little k is not the same as big K, but they are proportional. So little k is the retention or the capacity factor. If you see little k prime, it's the same thing. The retention factor is a measure of the number of moles of A in the stationary phase over the moles of A in the mobile phase. And it's also equal to the ratio of the time spent in the two phases. Now recall that TR is the total time that it takes to go from the entrance to the exit of the column. And TR is just T stationary plus T mobile. When you're in the column, you're either moving or you're not, right? So there's two different phases to be in. So I'm just going to take that and simplify it by plugging in T stationary plus T mobile minus T mobile over T mobile. And now we can clearly see that these cancel out to become stationary phase time over mobile phase time. Or in the textbook, you'll see this written as TR prime over TM. So the adjusted retention time. So in other words, if you have a greater concentration of that analyte in the stationary phase and it sticks to the wall with a greater affinity, right, you'll have a larger partition coefficient. But that will also mean that it takes longer to elute that compound from the column. So the Ks are proportional to one another. This alpha means proportional. So it's the same order, okay? I'm just going to modify this. So we're talking about little k. The retention factor would be greatest for arginine and it would be lowest for aspartate. And we just said that TR is greater for arginine than proline than aspartate. That's how we determine the answer for K. And TR is always total time, or TS plus TM. And then alpha, well, this is relative retention. And it's a ratio, it's unitless. It's a ratio of the retention time adjusted, or the stationary phase time, for any pair of analytes. They're separated in a column. And I'm just going to say that alpha would be highest for that which is most strongly retained, or for arginine. and alpha would be lowest for aspartate. So now with all this information, we can go and draw the chromatogram. And remember, chromatogram is some detection method used by an LC detector, like absorbance or perhaps refractive index, etc., as a function of retention time. And what you always see first, right, is a mobile phase peak. And then later on, we're going to have two other peaks. Now you might ask yourself, why don't we have 4 peaks? Well, in this first peak here, we get the mobile phase eluting. And oftentimes it comes out by itself first, right? It's unretained. Or it spends no time in the stationary phase. So TR prime for that is 0. But there's something else unretained in this, right? Aspartate, because it was anionic in the form of HA minus, does not stick at all to the anionic stationary phase. So aspartate is going to run out of the column as soon as it can. So I'll just color this one with the same colors we had above. That was aspartate. The next least retained would be the proline. And then finally, arginine is the most basic. Because it was in the form of H2A plus, whereas proline was HA, was Witterion. And therefore, this first value of time is Tm. And then you have TR1 and TR2 of the first and second eluting analytes. And the difference between the mobile phase and the first peak beyond the mobile phase is TR1 prime, or the adjusted, right, stationary phase time for proline. And this difference here between the first and third peaks is TR2 prime, or the adjusted stationary phase time of arginine. Okay. So the mobile phase in ion exchange chromatography is always something that is very polar, and it's generally water. Because it's so polar, it can dissolve and solvate ions. Hexane, which is a standard hydrocarbon solvent, C6H14 is the molecular formula, is completely nonpolar because it only contains sigma carbon-carbon and sigma carbon-hydrogen bonds. And there's no bond dipole in that structure. So it really destabilizes or will destabilize charged molecules. So the amino acids wouldn't even dissolve in them in the first place. And there's no such thing as a pH for a nonpolar solvent like that. So you cannot effectively separate them. So we said the amino acid that is most strongly retained is arginine, because it was the most basic. And the reason that it is sticking to the stationary phase is, of course, because of an ionic type bond between O- of the sulfonic acid and the positive charge of the diprotic form. So what you can do to eventually get this blue peak to appear is you can break this interaction. And that needs to be broken so that we can pull H2A off of the stationary phase. And certainly the way that you can break it is by making it neutral, or even going beyond that to make it negative. So you need to increase the pH or throw in some strong base to successfully deprotonate it. And at this point now it's anionic like aspartate and has no affinity for the stationary phase. So as pH increases, the Kpart and retention factor will decrease for protonated cations as they deprotonate. Okay, so then we have a couple of math problems involving these 3 amino acids. So you're told that TR is 3.5 for proline, 13.4 for arginine, and 1.2 for aspartate. And you're asked to determine K for each of them. And recall that K is the retention factor, which is simply the ratio of the stationary phase time over the mobile phase time. So first of all, for the aspartate, it's not retained. Right? In other words, TR is equal to TM. It comes out with the mobile phase. So K is 0. And we are going to use that TM value associated with aspartate for the other two calculations, because that is the first peak. So for proline, it's going to be 3.5 minus 1.2 over 1.2 is equal to K. So you get 2.3 over 1.2. Or 1.9. So it spends about 2 minutes in the stationary phase for every 1 minute in the mobile phase. And for arginine, this value is found by subtracting 13.4 minus Tm over Tm. So here I get about 10.2. So arginine spends about 5 times longer, or 5 times the amount of time in the stationary phase compared to proline. So the next question says, if 315 mils of mobile phase are required to elute proline, how many mils of mobile phase are required to elute arginine? So here we are talking about relative affinity of 2 analytes for the stationary phase. In other words, relative retention, which is alpha. And alpha is found by using the stationary phase times, either the adjusted stationary phase, the later over the earlier, which is the same as TR2, later peak, minus mobile phase, over TR1, the earlier peak minus the mobile phase. But if you do some simple math, that you can prove that this is just retention factor 2 over retention factor 1, or the retention factor of arginine over the retention factor of proline. And I found those values above to be 10.2 and 1.9 relative. So if you divide them, you get about 5.4. Or arginine likes stationary phase 5.4 times more. And therefore, we can say that the amount of volume of mobile phase required to elute an analyte is proportional to the duration of time spent in the column. Or TR. So what you can do now is say, well, if I know that arginine enjoys the stationary phase 5.4 times more, then the volume required to elute arginine should be 5.4 times more than the volume required to elute proline. Or we can solve for volume of arginine by multiplying over, and you'll find that 315 times that 5.4, or about 1690 mils are required is the volume of mobile phase to elute the arginine. Now, if you were to go ahead and increase the pH to deprotonate arginine, then you wouldn't need all that volume. This is assuming constant pH. Otherwise, the K value changes and you can't use this equation if the pH is changing. Okay. So then what percentage of the total time in the column does proline spend in the mobile phase? So we said that proline had a TR value of 3.5. And it had a TR prime, or stationary phase time, of 2.3. And the mobile phase time is 1.2. So the percentage of time in the mobile phase can be found from the retention time or from the capacity factor. And that's going to be the 1.2. Let me write it out in variables first. It'll be TM over total time times 100%, or 1.2 over 3.5 times 100%. So it's about 33%. So I get 34.2% there, time spent in mobile phase. And I've been talking about what happens when you add OH, but adding sodium hydroxide to the cation-exchange resin would cause what change in the TR of proline? So for proline, it was HA at pH 5, right? But if I add sodium hydroxide, then hydroxide is going to deprotonate and give water as a side product. So that means that we are going to now decrease the affinity of proline, because it's now fully basic. We'll decrease its affinity for the stationary phase, okay, or it's actually going to be repelled by the anionic stationary phase. So you would decrease the TR. In other words, you would decrease Kpart. There would be less of it in the stationary phase. You would decrease the retention factor as well. Okay, so one more question with these amino acids and then we'll move on. So how many grams of sodium hydroxide should be added to 145 mils of fully protonated Proline to set the pH at 10.5? So let me write out that equilibrium once more. And the pKa's for Proline were 1.99 and 10.6. So set the pH, right, means you have a buffer solution. That is the key verbiage in this problem. And I guarantee a problem like this will be on the final where you have to figure out the initial amounts of things to mix together to fix the pH. Even if they don't say the word buffer, right? You know it's a buffer if you have a fixed pH, especially if that pH is near one of the pKa's. It's quite close to 10.6. Now, we're not starting with the appropriate items for that buffer, right? In a buffer at pH 10.6, or sorry, 10.5, we are slightly more acidic than that pKa. So the major species barely is HA. And there's still a considerable amount, but it's the minor component that is A minus. But pretty much 0% is going to be in the form of H2A. You assume that a buffer really just constitutes of two main species. Although we are starting with fully protonated H2A, so we need to do a titration and add base so that we can take H2A and deprotonate it 100% with one equivalent of hydroxide. And then I can't stop at that equivalence point. That wouldn't be a buffer. I need to go some more and make some of the A minus so that I have a buffer of these two. So what you're going to do then is add some X amount, we don't know how much, of hydroxide to give the base. So to solve the problem, you have to write correct balanced reactions, and then we're going to use Henderson-Hasselbalch equation. So you first start with diprotic acid, and we know that it's going to react irreversibly with a strong base to give water, which will not affect the pH. And because it's a strong base, it's a one-way arrow or an ICF table. And I'm mixing stuff together. So I'm going to use moles or millimoles. I'll use millimoles in this table to avoid any strange changes in concentration. And the millimoles of H2A is equal to the molarity, 0.1, times the milliliter value, or 14.5 millimoles, the initial amount of H2A. And in order to go to the first equivalence point, I need 14.5 millimoles of hydroxide. That will only take me to the first equivalence point. So that's the minimum amount that I need. But I'm going to need some X amount beyond that, as shown here, to get into the second buffer region. And you don't start with any HA yet when it's fully protonated. But now we can see that the diprotic acid must be the limiting reagent in the first table. So that you are now left with two things, HA, which is Amphiprotic, and some X amount of strong base. So when you have an Amphiprotic species that can be an acid or a base, it will act as an acid in the presence of the strong base. And so we write another reaction to titrate into the second buffer region. Also a one-way arrow because it is a strong base, and the final amounts in the first table become the initial amounts in the next. For any buffer, we know that the pH, okay, is going to be a fixed value at 10.5 because you're going to have HA and A minus as the buffer components. And they're going to resist the change to pH that would occur if a strong acid or base were added. So what that means is at the end of any buffer problem, the strong base must run out. So I know that X is some value that is limiting. And therefore we can subtract X from HA and add X to A minus. And now we know that the pH, which is 10.5, should equal the nearest pKa plus the log of the base, A minus, over the acid. And that's in millimoles, but it's just a ratio. So if you subtract over, then you'll find that 10 to the negative 0.1 is equal to the ratio of base to acid. And that's 0.794. And if you do some simple algebra to isolate these, then you'll get that X is equal to 11.5 minus 0.794X. And therefore 1.794X is equal to 11.5. And this gives an X value of 6.42. So now, go back to the problem. We want to know how many grams of hydroxide initially we need to add. Well, we know that we need X equals 6.42 millimoles of hydroxide after that first equivalence point. So the total hydroxide we need is 14.5 initially plus X, right? This value here. Or 20.9 millimoles of hydroxide. And then to get to the mass in grams, you take 20.9 millimoles and you multiply it by the number of grams per mole. 40 grams in 1 mole. And then that gives you milligrams. So then you say, well, in 1 gram, there are 1,000 milligrams. So divide by 1,000 and then multiply by 40. Or 0.837 grams of NaOH. Okay, so be able to do those buffer problems. They are commonly on the final.